Hello everyone, and welcome to This Explainer. All right, let's jump right into this, because we've got an absolutely fascinating journey ahead of us today. When you look at the apps on your phone, the software running our global financial systems, or the complex code powering artificial intelligence, it feels entirely modern, right? Like it was just invented yesterday. But here's the secret. The modern code powering our entire world is fundamentally rooted in 9th century mathematics. It's crazy to think about, but today we're going to trace that incredible lineage. We'll look at the ancient blueprints of logic and see exactly how they evolved into the rigorous, highly structured methods that developers use to build complex software today.
So here's our roadmap for today. We'll start with the father of algorithms, explore his legacy of logic, and bridge the gap into modern computational thinking. Then we'll unpack the program development lifecycle and its 4 exact stages.
Let's get right to it. Section 1. The father of algorithms, the 9th century roots.
To really set the scene, we have to travel way back in time to the Islamic Golden Age. This was a period of just immense scientific and intellectual flourishing. And right in the middle of it all, meet Muhammad ibn Musa Al-Khwarizmi. He was a brilliant 9th century Persian mathematician, astronomer, and all-around scholar. Now, you might not hear his name every single day, but his work forever changed the trajectory of human history. He essentially laid the absolute bedrock for computer science as we know it today.
Think about the word algorithm for a second. It's literally the heartbeat of all computer programming, right? Well, that word is directly derived from the Latinized version of his name, algorithmi. So, every single time we talk about algorithms today, whether it's social media feeds or search engines, we are directly referencing this 9th century scholar's enduring legacy of intellectual achievement. How cool is that?
And honestly, he didn't stop there. He also gave us the word algebra. Yep, it comes straight from his groundbreaking book, Hisab al-Jebra wal-Muqabala. This book was a total game changer because it introduced systematic methods for solving linear and quadratic equations. He developed techniques for manipulating unknown variables, which effectively created the algebraic discipline that pretty much every high schooler studies today.
Moving on to Section 2, a legacy of logic. Groundbreaking contributions.
So Al-Khwarizmi didn't just write theoretical books. He provided highly practical, step-by-step procedures to solve real-world problems. And before we even get into complex calculations, we have to look at this absolutely fundamental contribution. He was instrumental in adopting and spreading the Hindu-Arabic numeral system. Basically, he introduced the decimal, positional number system and the concept of zero to the Islamic world. Think about that for a second. The digits 0 through 9, which gave us a vastly more efficient way of representing numbers and revolutionized arithmetic, that was championed by him. Computers literally speak in zeros and ones, and he helped bring the zero to the forefront.
His vast array of work brilliantly illustrates just how far ahead of his time he really was. We're talking about step-by-step formulas for computing areas and volumes of spheres and cubes, converting dates between Islamic, Julian, and Persian calendars, performing long division, and even calculating compound interest. Get this, he even developed algorithms for crypto analysis. That's the study of breaking codes and ciphers using frequency and pattern recognition. These systematic, logical approaches to problem-solving are exactly the kind of methods we use in modern computational thinking today.
Which brings us to Section 3, Modern Computational Thinking, Bridging the Gap.
So how do we actually take those ancient step-by-step mathematical concepts and apply them to building modern software systems? Well, to formulate a computer-based solution today, we use what's called computational thinking. We study a problem, kind of like Al-Khwarizmi did with astronomical tables or land boundaries, and we formulate an effective solution that a machine can execute. And to make this happen, we rely heavily on a couple of very specific techniques. Let's look at the first one. The first big technique is abstraction. Imagine just zooming way out. Abstraction is the process of extracting only the essential information and actively filtering out what is not necessary to solve the problem. Why does this matter? Well, abstraction gives us the power to deal with sheer complexity. By ignoring irrelevant details, the time it takes to develop a program is drastically reduced so it can be delivered faster. Plus, it means the final program is smaller in size, it takes up way less memory space, and it reduces download times.
The second core technique is decomposition. If abstraction is zooming out, decomposition is zooming all the way in. This is the process of taking a massive, complex problem and breaking it down into simple, manageable subtasks. And the benefits here are huge for sure. By breaking things down, the actual program code becomes so much easier to implement, test, and debug. It also allows different people on a team to be assigned to work on different modules simultaneously. And even better, those modules can often be reused in future programs.
Okay, let's look at a perfect, super simple example of decomposition. Say we want a program to calculate the sum of two numbers. We decompose that problem into standard logical components: input, process, and output. First, the input. We take in our two numbers, num1 and num2. Then, the process. We calculate the sum by adding them together. And finally, the output. We display the sum. Clean, simple, structured. Breaking a problem down like this is the absolute essence of computational thinking.
All right, Section 4, the Program Development Life Cycle, Structuring Solutions.
Now we introduce the overarching framework that houses all of this logic. And I want to pose a question directly to you, one that actually pops up in computer science exams a lot. What is the true purpose of the system development lifecycle? Like, why do we even need a rigid formal process for planning, creating, testing, and deploying systems composed of hardware and software?
Well, the answer is pretty straightforward, but absolutely crucial. In order to develop a successful program to perform a specific task or solve a given problem, the development needs to be well-ordered and clearly documented so that it can be understood and used by other developers. It's all about collaboration and order, because without a structured life cycle, software development would literally just be chaos.
So let's see how that order is maintained. Section 5, the 4 PDLC stages. Building the blueprint. Let's look at exactly how this well-ordered blueprint is built. There are exactly 4 stages in the program development lifecycle. They are analysis, design, coding, and testing. It's a linear cycle, and let's break down what actually happens in each of these critical phases.
First up, stage 1 is analysis. And notice something important here. We aren't writing a single line of code yet. This stage is all about gathering and interpreting facts and diagnosing problems. Developers will obtain end-user requirements through reading documentation, conducting client interviews, doing observations, or sending out questionnaires. They carefully scrutinize the existing system to keep the pros and avoid the cons. This is precisely where those techniques we talked about earlier, abstraction and decomposition, are first used to identify and define the exact problem and requirement specifications.
Next is Stage 2, Design. Here, the program specification from the analysis stage is used to show exactly how the program should be developed. We use decomposition again to break the problem into subproblems and then map it all out visually. Developers create structure charts, flowcharts, and write pseudocode. They also put together an identifier table to define the variables, constants, arrays, and any other data structures they'll need. Basically, this stage creates the complete architectural blueprint for the software.
Only now do we reach Stage 3, coding. This is the moment where the algorithms from the design stage are finally translated into actual machine instructions. The developer has to choose a suitable high-level programming language. They weigh the pros and cons of each language and decide which one they are most familiar with to best construct the solution. Once that's settled, they write the program code and begin their initial iterative testing and debugging. And finally, we reach Stage 4, testing. The code is written, but does it actually work? In this stage, the program is run many times using different sets of test data. The goal here is specifically to try and break it, to find errors and fix them. We need to definitively prove that the program does everything it is supposed to do, exactly in the way it was set out back in the original design stage. And that brings us to the end of our explainer. We've traced the blueprint of logic all the way from Muhammad ibn Musa Al-Khwarizmi in the 9th century, laying down the fundamental rules for algebra and algorithms, straight through to the rigorous 4 stages of the modern program development lifecycle. It really leaves us with a fascinating thought to chew on. If ancient manuscripts detailing things like long division and calendar conversions eventually gave birth to the incredibly complex software running our global digital infrastructure today, how will the algorithms of tomorrow reshape our world? Thank you so much for joining me to explore this incredible topic. Keep learning, keep questioning, and I'll see you in the next explainer.